Before Git, developers actually did this. Final to, final_real. So what changed? Version control solves one problem, remembering every past state of your project without renaming a single file. Older tools kept the real history on one central server. Lose that server, and you lose your history with it. Git is distributed. Every single clone holds the entire history. No network connection required to commit, branch, or look back in time. Git also does something unusual. It names every piece of data after the hash of its own content. This is called content addressing. Two identical files anywhere in history become the exact same object. Git never stores the same content twice. Because everything lives locally and is addressed by hash, most operations are just fast pointer math, not slow network round trips. Distributed, content, addressed, and fast. That is the whole bet Git made. And it is why almost every team runs on it today. Every commit you have ever made is actually just 3 kinds of tiny objects. Let's build one from scratch. Take index.html, Git hashes its raw content and stores it as a blob, named entirely by that hash. .style.css becomes its own blob, with its own hash. 2 files, 2 blobs, no relationship between them yet. A tree object ties them together. A simple list saying index.html points to this blob, style.css points to that one. A commit points at exactly one tree, plus metadata, who made it, when, and why. Written in the commit message? Edit only style.css and commit again. A new blob, a new tree, but the unchanged index.html blob gets reused exactly as is. The second commit also points backward to the first one. As its parent, that backward link is what makes history a chain, not a list. Blobs hold content, trees hold structure, commits hold snapshots plus history. Every single Git repository is built from just these 3. We said branches are cheap. Let's actually open one up and see why. Inside .-git's refs folder is a head subfolder. Open it, and main is just a plain text file. That file contains exactly 1 line, the hash of whatever commit main currently points to. That is the entire branch. Creating a branch called feature just writes a new file with that same hash copied in. 1 tiny file write. Instant. Commit while on feature, and only that one file gets its hash updated. Main's file does not change at all. Now open Hate itself. It usually just contains a line of text pointing at whichever branch file you currently have checked out. Switch to main, and Hate's text is rewritten to point there instead. Git then rebuilds your files from that branch's commit. Check out a commit directly instead of a branch, and Hate points straight at that hash. This is detached H-ed, still valid, just unattached to any branch name. Git tracks your files in 3 separate places at once. Most people only ever think about 2 of them. The working directory is just your files, as they sit on disk right now, however you left them. Run git add on a file, and its current state gets copied into a separate box, the staging area, also called the index. Git status is really just comparing these 3 areas. Stage changes are ready to commit. Everything else is still just sitting in your files. This is why git diff and git diff staged show different things. One compares working files to staging, the other compares staging to your last commit. When you commit, Git only freezes what's in staging into a new tree. Anything you never staged is simply left out of that commit. Edit 2 files, stage only 1, commit. The new snapshot updates just that one file. The other stays exactly as it was before. Working directory, staging area, repository. That middle box, is what lets you build a commit piece by piece, on purpose. .git log prints a clean list of history. But what is it actually reading to build that list? Every commit object holds exactly this: a pointer to one tree, a pointer to its parent, author info, and a message. .git log starts at whatever head points to, reads that commit's parent field, jumps there, and just keeps walking backward. A merge commit is special. It has two parent hashes, not one. Git log has to follow both paths to show the complete story. Notice two commits with the exact same files, but a different message still get different hashes, because metadata is hashed too. .git show just opens one commit object directly, then computes a diff against its parent tree, for display purposes only. So the entire concept of Git history is just this: a chain of small metadata objects, each one only knowing its own parent. .git log is not a database query. It is a walk, one parent pointer at a time, all the way back to the very first commit. A merge needs 3 commits to work, not 2. Where does that hidden third one come from? Main and feature both started at the same commit, then each moved forward on their own, picking up separate changes. To merge them, Git first finds their common ancestor. Walk backward from both tips until the paths meet a one shared commit. That is the third commit, the common ancestor. A merge is really a comparison between these exact 3 points. For each file, Git checks, did only one side change it since the ancestor? If so, it just takes that side's version. No conflict. But if both sides change the very same lines differently, Git cannot guess which one you want. That is a conflict. Those angle bracket markers are just showing you both versions side by side, so you can pick, combine, or rewrite them yourself. Once resolved, Git creates one new commit with 2 parents, both original tips permanently recording that this merge happened. So a merge is not a mystery. It is one shared ancestor, 2 divergent tips, and a careful line-by-line comparison between all 3. Rebase says it replays your commits. What does replaying a commit actually involve? Feature has 3 commits built on an older version of main. Main has since moved on, several commits ahead. Rebase starts by setting A, B, and C aside as pure changes temporarily detached from the chain they were built on. Feature is moved to sit on main's new tip. Then commit. A's changes are reapplied there, creating a brand new commit, A prime. B and C replay the same way. Every one gets a new hash because a commit's hash depends on its parent, and the parent just changed. The original A, B, C are not deleted immediately. They are just orphaned. No branch points at them, so Git will clean them up eventually. Interactive Rebase lets you edit this replay. Squash 2 commits into one, reword a message, reorder, or drop a commit entirely. The rule stands. Rebasing gives every commit a new identity. Do it on a branch someone else already has, and your histories will no longer line up. So Rebase is not magic editing. It is detach, move, and faithfully replay, with a brand new hash for every single commit. Your laptop and GitHub are not magically in sync. Something specific has to move data between them. What? Cloning copies the entire object database and every ref from the remote straight into your own local .git folder. Git also keeps a remote tracking branch, like origin/main, a local snapshot of where the remote's branch was, last time you checked. .git fetch downloads, new commits, and move that remote tracking pointer forward. Your own local main branch does not move at all. .git pull is just fetch, plus an automatic merge of that remote tracking branch into your current one. 2 steps wearing one name. .git push sends your new commits to the remote and asks it to move its main pointer forward to match yours. If origin has commits you never fetched, your push gets rejected. Moving its pointer forward would silently erase history you haven't even seen. Fetch downloads safely, pull downloads and merges. Push uploads and can be rejected. All three are just moving pointers, carefully. 8 chapters, 1 hidden folder. Let's put the whole model back together in 60 seconds. It starts with objects, blobs for content, trees for structure, commits that snapshot a tree and point to a parent. Branches are just tiny files holding one hash. Heading points at whichever branch or commit you're currently standing on. Your edits move through 3 areas: working directory, staging area, then repository, only when you commit. Merge finds a shared ancestor and combines both sides honestly. Rebase detaches your commits and replays them cleanly with new hashes. And remotes are just another copy of this same object store, kept in sync with fetch, pull, and push. Objects, refs, staging, commits, merges, rebases, remotes. Not magic, just a very well-designed graph of pointers and hashes. Like and subscribe for more.